Hi, welcome to Process Your Data with Graph Neural Networks. I'm Alejandro García, Head of Product Development at Foxrane, which some of you may already know. And I'm going to start this presentation by giving you an introduction on what are graphs and how we can use them with AI. Then afterwards, Velisarios, my colleague, will give you a bit of a practical view or a demonstration on how to do that. Okay, so I'm going to start by showing the differences between tabular data and graph data. Let's say that we have a data set with transactions, a transactions data set, and we have like bank accounts that they have movements from bank account A to bank account B by X amount of money, right? So we have different accounts that send X amount of money to another account. In a tabular data set, this will show by rows, right? So basically, like we can see in the image on the upper part, like the source A, the source bank account A will send X amount of money to the target. The most important part of this is that these data points will not be related in any sort of way as the first side. However, if we model it as a graph, in this case, the transaction data set will be modeled by B would be a bank account and A will be another bank account. So they will be the nodes of the graph. And the transactions will be the edges of this graph. So if there's a transaction from bank account A to bank account B, then these two will be related in the graph. So this is some way of introducing more information into the data set. It's kind of doing data augmentation at some point. Okay, so where are these graphs used nowadays? Well, they are, for example, used in human gene co-expression. So genes or proteins that make the genes are represented as a graph to identify which will be the feature represented in the body. So for example, to identify a disease. And this is really powerful in the scientific area because if you model these proteins as a graph, then it's much easier, or it's rather easier to identify which will be the disease that will be expressed. Another field is in chemistry, where you simulate the molecules in a graph, and then you try to predict which will be the material properties that this molecule representation will have. Another field is knowledge graphs. Search engines use these heavily. For example, to give you the best source of information, what they use is a knowledge graph that will take your query that you have inputted in their engine, and then they will, from all this information that they have from web pages, from dates, from people, they will try to put this and give you the best source of information for what you asked for. Also, this can be used for marketing, where you can actually model people's behavior as a graph, and then you will get like an advertisement, or well, if you don't want the advertisement, you can actually get an offer. That will be much interesting, just heads on that. Okay, so another really interesting approach is modeling the face. This could be done for facial recognition. So imagine that you have two nodes for the eyes, one node for the nose, and then 2 or 3 nodes for the mouth. And these nodes are related in a way that will give you the best representation for your face. So if these two nodes move like this, then you're probably smiling, right? So the fact that these 2 or 3 nodes are connected as an edge or with an edge, it will give a much easier way for the model to detect that you're smiling. It can also be used for the entire body, where you can have a node for each part of your body, and then the edges will be connected as the limbs, for example. And then you can actually detect what is the activity that you're doing, or if you're running or just walking, and all sorts of stuff. Also, it can be used for robotics in order to model the best way to walk, for that robots can walk like us in someday, for that to know. Okay, a really interesting one is transport networks. So this can be seen as the flights from one place to another. However, a more interesting approach is looking at the logistics network. The logistics network is a really interesting for graphs because you have different packages that need to be delivered from point A to point B. And there's a lot of other transportation systems like trucks or boats or flights. And in order to make these packages go from point A to point B, it's really interesting to model this transport network as a graph, because you can have actually the shortest path or to optimize this path more easily. So it's really interesting for the logistics to model their transport network as a graph, basically. Another actually really interesting way or field is the telecommunications network. As far as we know, this is not done nowadays, but it will be really interesting to model the telecommunications network as a graph. Because imagine that each tower is a node of a graph, and then each handover that a mobile phone does from one tower to another would be an edge. In this way, you would be able to model the whole network as a graph, giving you a much bigger perspective of what's happening in the network and probably detecting and identifying anomalies much easily instead of modeling each tower by itself, which is basically done nowadays. Okay, so we have seen a lot of the different applications that have been done with graphs, but this is not the only thing that has been done. Like the graph theory is a very mature field, and it comes from this 1878, and a lot of different algorithms have been developed, like the Dijkstra shortest path, the Bellman-Ford algorithm, Floyd-Warshall algorithm, shortest path, graph cycles, and connectivity. So we can see that the number of approaches and applications is manifold. However, the most novel one and the one that we are here for is because of AI, right? So let's put it this way. The most successful models that we have nowadays with deep learning is basically in computer vision. And an image is basically a 2D representation of your data. So a convolutional neural network, which is the most common one in computer vision, what it basically does is it gets one pixel of the image and its neighbors, and then it adds them and it puts them in the next layer to form a new latent space, right? However, an image can be modeled as a graph, where each pixel of the image will be a node, and then you can have edges from each pixel or node to the closest neighbors. So basically, if we do that, we are actually using a graph with convolutional neural networks, right? Where each pixel will have the corresponding neighbors or node neighbors in the next latent space. So by showing that, we show that with convolutional neural networks in images, we are basically using graphs. So now we have shown that we can use deep learning in graphs. And there's a lot of different architectures that have been developed in deep learning, like attention networks, convolutional networks, adversarial networks, and these can also be used in graphs. And the number of applications is also massive. We can actually do anomaly detection for the nodes or the edges, prediction of new nodes, generating new graphs based on the input, or even finding the shortest path in a really fast way. So as we can see, the application is also manifold. So now that I have explained and introduced you to graph neural networks, I'm going to let Velisarios demonstrate how we can use them with a demo that we have prepared.
Hi everyone, my name is Velisarios. I am a data scientist and co-founder of Foxrane. I will be taking over from Alejandro with my thanks, and together we will be taking a look at some practical applications of the graphs and the graph neural networks that Alejandro has been talking about. Specifically, we will be taking a look at a data set that we have prepared, which consists of a network of devices that are spread around in Stockholm, and how we can take advantage of the fact that those devices speak to each other to create a neural network which predicts some KPI that we're interested in. Let's go ahead and take a look at that graph. So Right now we're looking at Immerse. Immerse is a visualization layer built on top of OmniSci. OmniSci is a database, is a CPU accelerated database which is used for analytics purposes, and it makes working with very big data sets a breeze because it is very fast. We can move around in that area, taking a look at the graph very easily. None of those things are pre-calculated, none of those views are pre-calculated, they're all created and rendered on the fly. Now, for the graph specifically, let's zoom in here a bit. You can see that it consists of a number of nodes. Those are represented with a little green crosses, and each of those crosses is speaking to some of its neighbors across the blue lines. That blue line represents some kind of data stream that the nodes use to exchange messages. So, as I said before, those nodes can be thought of as some kind of device. That device can either be just some IoT device, it can be a phone tower in a mobile network, it can be some kind of vehicle, or it can be the driver in a delivery van which who has some kind of device that is able to speak to the other vans around it. In any case, this graph represents a use case that is pretty common, but it also has the geographical element, so it places the nodes on the actual physical world, which makes it easier to see the possibilities and the capabilities of the graph neural networks that we'll be talking about. Specifically, we are interested in predicting some kind of KPI at the nodes. That KPI can be some kind of throughput measure or some kind of latency measure, or it can be some delay, or it can in general be some kind of health metric for that specific node. And we know that this metric, this KPI, is affected by the traffic that comes into that node. So the number of messages that are coming into a specific node from its neighbors, and of course the number of neighbors that the node is connected to, is really important in our attempt to predict that KPI. In that dataset that we're looking at, we have actually some historical data about those specific KPIs. Over here, we're looking at a snapshot in time of that graph, and we can see that the nodes are now colored according to that KPI. Abstractly, we can think of the color of the node as representing the health of the node. The redder the color, the sicker the node might be. We do not want our nodes to be sick. We actually want them to be healthy, and we want them to be performing their duties to their fullest extent. So we would like to be able to predict the effects a change in the network would have on each specific node. So we would like to, for example, send some traffic over the network and see how the network would react. Or we would like to get get a snapshot of the graph, figure out how it is going to look at some point in the future based on in the snapshot that we got, and based on that prediction make some decisions. So basically we would have that graph neural network as part of an automation pipeline, which makes decisions on its own according to the health of the nodes in the network. To achieve all that, we need to write some code. So let's go ahead and take a look at some code. We will be using Julia for that for this demo. Julia is a programming language that we are pretty fond of here in Foxrane. It is very performant, and it has a very large ecosystem of packages that are doing all sorts of interesting things. It is performant because it is just-in-time compiled, and there is a lot of work being put into the packages of the ecosystem, because it is very much used in academia. So people are writing their physics experiments with Julia. They're writing their neural network experiments, and so on and so forth. But it is feature complete. And to begin with, we're going to use it to read in some pre-prepared files. So we have already created an adjacency CSV, which basically this file just describes the connections between two different nodes. It tells us which nodes are connected. And we have also created a features file, which consists of an encoding of the traffic that the network experiences. So we go ahead and read both of those files into some data frames. Those data frames, you might be familiar with them from Python. They work very much the same way in Julia as well. And now that we have read those two files, we can go ahead and create the graph. To do that, we will use another package called Light Graphs, which is a very lightweight package, and it is developed with that aim in mind. It is very easy to use, and it is very easy to integrate into other packages. So to create our graph, we define a simple graph which has the number of nodes of our network. And then we just iterate over our adjacency matrix, and we pick out its edge as defined in that adjacency matrix, and we add it to the graph. You can see here that we add the node of origin and the destination node, and at the end of that for loop we are left with a graph. As you saw, that was very fast, because Julia does not punish you for using for loops. I very much encourage you to look into it. Now that we have our graph, let's go ahead and take a look at it. So hopefully here in that image you can see that we're actually working with a graph, but the geographical dimension is completely lost. Of course, that graph, that representation is also absolutely non-interactive, but a very big aspect of that specific dataset is completely lost in that kind of representation. That is why we are very much fond of using tools like OmniSci to take advantage of the geographical dimension. But let's go ahead and transform our graph into an adjacency matrix. An adjacency matrix, as the name suggests, is a matrix which has the same number of rows and columns, and each of the cells takes one of two values, either 1 or 0. It takes the value 1 if there is a connection between two different nodes, otherwise it takes the value 0. And we need to use that because we're going to do some we're going to train a neural network, and a neural network is just a pile of linear algebra, so we really like matrices when we're doing linear algebra. To train the network, we're going to use Flux and geometric Flux. Flux is the main package in Julia to train neural networks, and geometric flux is an extension that allows it to train graph neural networks. We have defined some constants. The first one is the number of features. That is the encoding of the traffic that comes into its node. And we also define our KPI. Our KPI can take one of 7 values. As with every other neural network, we're going to be normalizing our input and creating one-hot vectors of our labels. Those features and labels will be our training data, which we load into the GPU. Flux is also GPU accelerated, and it allows us to take advantage of parallel computing very easily. And we will be defining the model. This model is very simple. It's not very deep. It's not very impressive. In any case, it consists of a couple of graph convolutional layers separated by a dropout layer and then a softmax on top, so that we can get predictions out of it. As Alejandro was saying, the convolutional layer in the graph context is pretty similar to a convolutional layer in the image processing context, but it also takes into consideration the adjacency matrix, so it takes into consideration the actual graph structure of our data. Our loss is just the cross entropy loss, and we're going to train using the Adam optimizer. Now, this training process is going to take a while, so we're not going to spend a lot of time waiting for that network to train. We have trained a similar, if a bit bigger network in the past, and we have gotten some predictions out of it, which is what we're going to be looking at in a second. But let's give it let's give it a minute to so that we can get some output from it. So the end of the first epoch, we're not expecting a lot of accuracy, but it increases quickly. It does not reach state-of-the-art levels, but it definitely is very much usable. Let's go ahead and take a look at the output of a pre-trained model. So this representation looks very much like the one we were looking at before, but now we have a time component. So we used past data to train a model to predict the state of its node when some changes happen in the network. And by sliding over the time dimension, we can see that the network changes. The network changes because the traffic across the edges changes, and thus the nodes get different, report different KPIs, right? They become healthier, or they become less so based on the traffic that is coming into them or going out of them. And the health, the KPI of its node affects its neighboring nodes, because as I was saying before, if the KPI we're interested in is throughput, then the output of a node is going to be reduced. So the traffic that travels along an edge is going to be reduced as well, and that will affect the KPI of the neighboring tower. That kind of interconnectedness, that kind of ability to take advantage of the behavior of the neighbors is very hard to encode in neural networks, or it has been very hard in the past. The first attempts at doing that were based on recurrent neural networks, and there is a reason why those have fallen out of favor. But using this kind of approach that we saw today can yield some very powerful results when you're looking, when the use case that you're interested in can be represented as a graph. And as Alejandro was saying, a surprising number of use cases can actually take advantage of the graph structure. So I urge you to look into neural net or graph neural network solutions for your use cases, whatever those might be. Thank you very much. I hope you enjoy the rest of the conference.